As an operator in an industrial facility, you're responsible for the safe and efficient operation of the systems in your plant. To do your job, you have to understand how these systems operate and how they're controlled. One way to get this information is by using diagrams. One type of diagram you're likely to use is a piping and instrumentation diagram, or P&ID. The information on P&IDs is helpful when you're learning about a new system, as well as when you're troubleshooting a system that you're familiar with. And when P&IDs are revised because changes are made to systems, they're helpful when you need to learn about system modifications. P&IDs help you identify instrumentation that's used to monitor and control conditions in process systems. The diagrams also tell you if the instruments are located on a board in another area or near the equipment. For instance, this symbol represents a flow recorder controller. This line indicates that the symbol represents a remote instrument, one that's mounted on a board in a remote location, such as in a control room. P&IDs help you identify instrumentation that's used to monitor and control conditions in process systems. The diagrams also tell you if the instruments are located on a board in another area or near the equipment. For instance, this symbol represents a flow recorder controller. This line indicates that the symbol represents a remote instrument, one that's mounted on a board in a remote location, such as in a control room. A circle without a line through it represents a local instrument that's mounted near the system it's associated with. A circle with two crossed lines is sometimes used to represent a transmitter. Transmitters are typically mounted locally. Sometimes an instrument symbol also contains an identification number that helps you distinguish it from similar instruments in other systems. Generally, all the symbols for the instruments in a control system will contain the same number. This helps you identify all the instruments that belong to a particular system. P&IDs also give you information about the types of piping in a system and how each type is represented. Piping sizes are also noted on many P&IDs. Knowing the type of piping and its size can be useful when you're tracing a system in the plant. To get an idea of how you can use P&IDs to learn how systems work and how they're controlled, we're going to look at P&IDs for a water treatment system. But before we get to the details shown on the P&IDs, let's look at another diagram, a block diagram, to get an overview of the system. This is a block diagram of the water treatment system. The system consists of a chemical mixing section, a clarifying section, and a clear well section. The inputs to the chemical mixing section are lime, alum, and treated water. This section produces an alum solution and a lime solution. The two solutions are sent to the clarifying section. Raw river water enters the system in the clarifying section, where it's mixed with the solutions from the chemical mixing section. The alum causes solid materials in the water to clump together so that they can be removed. The lime is used when the pH of the water is lower than normal. It raises the pH and makes the water less acidic. The clarified water enters the clear well section, where most of the remaining solids are removed. The treated water is then sent to a storage tank. Now that we've seen how the three sections of the water treatment system are connected, let's look at the P&IDs for each section. We'll start with the chemical mixing section. The chemical mixing section is actually made up of two separate chemical systems, an alum system and a lime system. Let's look at the lime system first. The equipment in the lime system includes a dry lime hopper, a motor-driven shaker, and a mix tank and mixer. Lime is added to the hopper manually. The shaker dispenses the lime from the hopper into the mix tank. Treated water enters the system through this piping and is fed to the mix tank. The line symbol indicates that the treated water line is made of copper. The mixer mixes the lime and water. The mixture then flows out of the mix tank. The line symbol indicates that the mixture flows through a rubber hose. A control system starts and stops the lime system based on the pH of the raw water from the river. The control system has an analyzer transmitter that measures the pH of the river water. As you see here, this type of transmitter is sometimes represented by a square rather than by a circle. The dashed lines shown here are a common way of representing an electrical signal line. The transmitter sends an electrical signal to a pH recorder controller. The pH recorder controller records the pH of the raw river water. When the pH of the raw water is too low, the controller sends an electrical signal to the solenoid-operated control valve, to the mixer motor, and to the motor on the lime shaker. The control system has an analyzer transmitter that measures the pH of the river water. As you see here, this type of transmitter is sometimes represented by a square rather than by a circle. The dashed lines shown here are a common way of representing an electrical signal line. The transmitter sends an electrical signal to a pH recorder controller. The pH recorder controller records the pH of the raw river water. When the pH of the raw water is too low, the controller sends an electrical signal to the solenoid-operated control valve, to the mixer motor, and to the motor on the lime shaker. The solenoid opens the valve to admit water to the tank, and the two motors start to operate. As treated water and dry lime enter the tank, the mixer mixes the water and lime. The mixture flows out of the tank to the clarifying section. Now let's look at the alum system. To make a solution of alum in water, the operator first adjusts the flow recorder controller to close the alum solution control valve. Then he opens a valve to add a concentrated alum solution to the mixing tank. On this diagram, the storage tank isn't shown. A note indicates the source of the alum. Using the sight glass on the tank, he monitors the level in the tank until the level corresponds to the amount needed to make a full tank of alum solution. The operator then adds treated water to fill the tank. The mixer in the tank stirs the solution. Then the operator readjusts the flow recorder controller to reopen the control valve. This symbol represents an orifice plate in the river water piping. The symbol containing the letters FT represents a flow transmitter. The transmitter is connected by tubing to the water line on each side of the orifice plate. The transmitter compares the pressures on the two sides of the plate to determine the rate of flow in the pipe. The flow transmitter then sends a pneumatic signal to the flow recorder controller. The recorder controller sends a pneumatic signal to this flow control valve located in the line from the alum mixing tank. The valve regulates the flow of alum solution to the clarifying section based on the flow rate of river water entering the system. The line symbol indicates that the alum solution piping is made of PVC plastic. If a test shows that the wrong amount of alum is being sent to the clarifying section, the operator adjusts the flow recorder controller. This changes the flow through the alum solution control valve to correct the problem. The alum solution and the lime solution flow to the clarifying section, as the notes on the diagram indicate. That section is represented on a separate P&ID. This P&ID shows that the clarifying section consists of a single vessel with 3 compartments: a flash mixer, a flocculation basin, and a sedimentation basin. Raw river water enters the system here in the flash mixer, where it's mixed with alum and lime from the chemical mixing section. The alum causes suspended solid material in the water to begin to clump together. The lime raises the pH of the water when the pH is lower than normal. The flash mixer compartment contains a motor-operated mixer. This symbol represents an analyzer transmitter. It measures the pH of the water in the flash mixer. We can tell that it measures pH because it's connected to this pH indicator recorder. The mixture of water and chemicals in the flash mixer overflows a weir and enters the flocculation basin. In the flocculation basin, the water and chemicals are stirred gently by this large mixer. Here, the clumps of solid material grow larger. From the flocculation basin, the water and solids overflow another weir into the sedimentation basin. Here, the clumps of suspended solids settle out and form a sludge on the bottom of the basin. This symbol represents a motor-operated sludge rake that moves the sludge to a trough at one end of the basin where it can be removed. A level transmitter senses level in the basin and sends a signal to a level recorder controller. The recorder controller sends a pneumatic signal to the positioner on a control valve. The valve controls the level in the sedimentation basin by regulating the flow of river water that enters the clarifying section at the flash mixer. From the sedimentation basin, the clarified water leaves the clarifying section and goes to the clear well section. The major components in the clear well section are a gravity filter and a clear well. The gravity filter removes the small amount of solids that haven't settled out. Water enters the filter through this line and leaves through this line. This symbol represents a pressure differential transmitter. The transmitter receives pressure signals from the two connections located on the filter. The transmitter produces a pneumatic signal that's proportional to the difference in pressure across the filter. The transmitter signal goes to this remote pressure differential indicator. When the difference in the pressures measured at the two pressure connections on the filter reaches a predetermined value, it means that the filter has become clogged by trapped materials. When this happens, the filter must be taken out of service so that it can be cleaned. To clean the filter, this isolation valve is closed to stop flow into the clear well, and the filter is backwashed with treated water to remove the trapped material. Then the filter is returned to service. This symbol represents a local level switch. If the water level in the filter drops below a certain level, the level switch sends an electrical signal to this motor-operated gate valve. The valve closes to stop water flow out of the filter, because if the filter runs dry, it won't work properly. These symbols represent the components of an instrument system that records the flow of water to the clear well section. The clear well holds the treated water until it's sent to storage. Level in the clear well basin is sensed by this level transmitter. The level transmitter sends a pneumatic signal to a level recorder controller. The recorder controller sends a signal to this pneumatic globe valve. The valve controls the flow of water into the clear well basin. From the clear well basin, the treated water leaves the system and goes to a storage tank. In this part of the program, we looked at the general types of information that can be found on P&IDs, and we used a set of P&IDs to become familiar with the system and its instrumentation. Try some practice questions now on using P&IDs. In this part, we'll look at troubleshooting a problem that's been noticed in the clarifying section of a water treatment system. The purpose of the clarifying section is to take in water from a river, remove solid material that's suspended in the water, and adjust the water's pH. Before we get to troubleshooting the problem, let's take a look at the P&ID for the clarifying section to see how it operates. On this P&ID, we see that the clarifying section is divided into three sections. In the first section, called the flash mixer, river water is mixed with alum and lime solutions from a chemical mixing section. The alum causes solid materials suspended in the water to clump together and settle out. The lime raises the pH of the water, making the water less acidic. From the flash mixer, the water overflows into a flocculation basin, where the clumps of solid material grow larger. From the flocculation basin, the water overflows into a sedimentation basin, where most of the solids settle out and are removed. The water flows out of the sedimentation basin to the clear well section, where the remaining solids are removed. These components control the flow of water through the clarifying section to prevent the sedimentation basin from overflowing. Now, the problem we'll consider is this. An analysis of the water in the clarifying section shows that the pH of the water is not being adjusted properly. If the problem is not corrected, the process that uses the water from the system will be affected. These components control the flow of water through the clarifying section to prevent the sedimentation basin from overflowing. Now, the problem we'll consider is this. An analysis of the water in the clarifying section shows that the pH of the water is not being adjusted properly. If the problem is not corrected, the process that uses the water from the system will be affected. Since our problem involves the pH of the water, we'll focus our attention on the flash mixer, because that's where the pH is adjusted by the addition of the lime solution. This analyzer transmitter measures the pH of the water in the flash mixer and sends a signal that represents the pH to this indicator recorder. The pH indicator recorder is currently indicating that the pH of the water is too low. We can use the diagram to identify the equipment that could malfunction and cause the pH to be lower than it should be. The lime solution from the chemical mixing section is carried to the flash mixer by a rubber hose. So the hose could be checked for clogs or leaks. If the hose is okay, we would need to check the components at the other end of the hose, in the system that makes the lime solution. It's common to have to trace flows upstream to other systems to locate the causes of problems. This often means that more than one P&ID may be needed to troubleshoot a problem. For our problem, we'll need to look at the P&ID for the chemical mixing section. This P&ID shows the components of the chemical mixing section. This symbol represents the hose to the flash mixer in the clarifying section. The lime solution carried by the hose is made in the mix tank of the lime system, so the tank and its motor-driven mixer could be checked for visible problems. Lime is added to the mix tank by this motor-driven shaker, so the shaker could be checked to see if it's clogged or damaged. The motor could also be checked for problems. Lime for the shaker comes from a hopper that's filled manually, so another thing to check is whether the hopper contains a supply of lime. Treated water used to make the solution is added by opening this control valve in the treated water supply line, so the valve could be checked for proper operation. Since the system is controlled by this pH recorder controller, it could be checked. Finally, we could trace the electrical conduits from the lime system to the pH recorder controller and back to the analyzer transmitter, looking for damage that might indicate an electrical signal problem. After the components that could be causing the problem have been identified, the components can be inspected to locate the problem. In this case, the problem turned out to be a bad electrical connection at the lime shaker motor that kept the motor from operating properly. The P&IDs helped us focus our troubleshooting on the components in the system that could be associated with the problem. In this part, we'll look at a troubleshooting problem in a water deaerator system. The system is designed to remove dissolved oxygen and other gases from a supply of water. The deaerated water is then fed to a boiler. Before we get to troubleshooting the problem in the system, let's take a look at the deaerator system P&ID to see how the system operates. This is the P&ID that represents the deaerator system. This symbol represents a heat exchanger that heats the water. This one represents the deaerator itself. And this one represents a deaerated water storage tank. Water flows into the heat exchanger, which uses steam to heat the water. Then the water flows out of the heat exchanger past this device. This symbol represents a local temperature indicator that indicates the temperature of the water leaving the heat exchanger. Next, the water flows through an arrangement of valves. This particular valve is called a level control valve. It's called a level control valve because its purpose is to control the level in the storage tank. From the valve arrangement, the water enters the deaerator. Steam is supplied to the deaerator through a gate valve. In the deaerator, the steam strips dissolved gases from the water. The steam and gases leave through this vent line. And deaerated water flows out of the deaerator to the storage tank. The deaerated water storage tank has a temperature indicator, a level gauge, and a level transmitter. The level transmitter is connected to a level controller and to a level alarm system. The controller is connected to the deaerator level control valve that regulates the flow of water into the deaerator. Steam is supplied to the deaerator through a gate valve. In the deaerator, the steam strips dissolved gases from the water. The steam and gases leave through this vent line. And deaerated water flows out of the deaerator to the storage tank. The deaerated water storage tank has a temperature indicator, a level gauge, and a level transmitter. The level transmitter is connected to a level controller and to a level alarm system. The controller is connected to the deaerator level control valve that regulates the flow of water into the deaerator. These symbols represent level switches that are connected by electrical signal lines to this remote level alarm. If the level in the storage tank gets too high or too low, one of the level switches activates the alarm. The deaerated water leaves the storage tank through this line. Now let's look at the troubleshooting problem. In this example, the level alarm on the deaerated water storage tank indicates that the level in the tank is either too high or too low. So the first thing to do is determine the actual level. That's done by checking the level gauge on the tank. In this case, when the level gauge on the storage tank is checked, the level is found to be okay. Next, we need to consider the possible causes of the false level alarm. Let's identify the components that could cause the alarm to incorrectly indicate a level problem in the tank. First, we could check the level transmitter. If there's a problem in the transmitter, it may send a false signal to the other instruments in the level control system. The pneumatic lines that connect the instruments in the level control system can be checked for leaks or damage that could interfere with the signal transmission. The low-level switch and the high-level switch should be checked to see if they're working properly. Since the level alarm has been activated, the level alarm and its connections to the level switches should be okay. When the components in the system are checked, the problem turns out to be a faulty level transmitter that's sending a false high-level signal to the rest of the components in the control system. In this case, the alarm alerted us to a problem early enough that we were able to locate the problem before it had a major effect on the operation of the system. In this part of the program, we've used P&IDs to troubleshoot operating problems in a water treatment system and a boiler water deaerator system. Try some practice questions now on using P&IDs to troubleshoot system problems.